Design and simulation of silicon nanowire-based Nano Capacitive Pressure Sensor. Abstract. This paper presents a nano capacitive pressure sensor with enhanced sensitivity using silicon nanowires. The work presented here reports the design and simulation of nanowire-based capacitive pressure sensor for human blood pressure measurement. Usually ordinary circulatory pressure of a human is 120/80 mmHg. This range can deviate if a person has hypertension or any other medical issues. Hence this pressure measurement is a very first thing that is done before any diagnosis or treatment. Many conventional devices exist to measure the pressure, and also digital devices are now being commercialized for measurement. The accuracy with which these digital devices function is always a concern. In this paper we present a nanowire-based cap-active pressure sensor which can operate efficiently over the pressure range of 0 to 300 mmHg. A equivalent pressure of around 40 kPa pressure is applied on the sensor for measurement, and the sensor shows a good sensitivity of 2.5 x 106 pf/kPa. Keywords: MEMS, sensor, pressure sensor, nanowire, capacitive pressure sensor. Introduction. Nanotechnology is a very rapidly growing technology for development of nano-sized sensors and actuators. There is a lot of works reported on MEMS-based pressure sensors. Capacitive pressure sensors are well suited for low-pressure sensing applications. Works in 1, 2, 3, 4, 5 describes the development and analyses of MEMS-based capacitive pressure sensors. Silicon nanowire-based capacitive pressure sensors are gaining high attentions because of their small dimensions and better sensitivity. Nano sensors are probably going to affect our economy and society a lot, and the technology, practically identical to that of semiconductor innovation 6. The nanowire is largely suitable development of biosensor/biomedical sensors, as the properties of silicon nanowires depicts that they are mechanically, electrically stable. 7. Silicon nanowires-based transistors are developed by authors in 8. Silicon nanowires are largely used for biomedical sensing applications. One such example, where the sensor was developed for carotid blood pressure of horses 910. Currently, most common disease is high blood pressure. This can be detected using miniature pressure sensors 11-12. A micron-sized capacitive pressure sensor with 3 m electrode spacing was developed by authors 13. Other applications where nanowire sensors are used are intraocular pressure, intracranial pressure measurements were mostly short-term measurements. For long-term implantable pressure sensors, the influence of biological environment should be considered. 14, 15, 16, 17. Among the wide sector of biomedical sensing applications that the silicon nanowire sensors have been used for, some of them are applied to physiological body movements 18, human heartbeats 19, blood flow 20, pulse rate 21, drug delivery 22, protein 23, tumor detection 24, DNA sensing 25, and stem cell research 26. The idea of using nanowires in piezoresistive pressure sensors has been reported in literature, but these sensors are suited for high-pressure sensing. Capacitive sensors are reported to be best suitable for low-pressure sensing applications. In this work we report the design and analysis of silicon nanowire-based capacitive pressure sensor for human blood pressure monitoring. The pressure range considered varies from 0 to 300 mmHg, which is approximately equal to 40 kPa. The device provides a sensitivity of 2.5 x 10⁶ pf/kPa. In the next sections the design, simulation, and analysis aspects of the sensor is discussed. 2. Design of silicon nano-capacitive pressure sensor. The sensor is optimized for pressure sensing range of 0 to 40 kPa using theory of plates 27. The sensor is a parallel plate capacitive pressure sensor, using free and fixed electrodes respectively. The top, free electrode, is completely made up of array of silicon nanowires. Air is considered as the dielectric material. The bottom plate is made up of aluminum. Fig 2.1 shows the designed sensor. The sensor is designed using COMSOL/multiphysics. The dimensions used for the design and modeling of the sensor is mentioned in Table I. Table I. Dimensions of the nano-capacitive pressure sensor. Material properties play a very important role in efficient behavior of these sensors. The materials properties considered for the simulation and analysis of the nano-capacitive pressure sensor are mentioned in Table 2. Only important properties are mentioned in Table 2. Table 2. Material properties. Parameter value. The complete view of the sensor is shown in Fig 2.2. The sensor image shown is the simulation model taken from COMSOL/multiphysics. The top of the sensor showing the array of silicon nanowires is shown in Fig 2.3. 3. Simulation and result discussion. A simulation environment. The model shown in Section 2 is simulated using COMSOL/multiphysics using electromechanics physics. A square diaphragm is considered for simulation as it provides better stress/strain distribution. The model dimensions and the material properties used for simulation are mentioned in Table I and Table 2, respectively. A free tetrahedral meshing is employed on the sensor for FEM analysis. The parameters considered are mentioned in Table 3. As boundary conditions on top plate, a known variable pressure of 0 to 40 kPa is applied and temperature is kept constant at 25. The sensor is biased with an external voltage of 1V. Silicon nanowire array is placed as top electrode, where each nanowire is of 300 nanometers in length, 1 nanometer in width and thickness of 2 nanometers. Each nanowire is separated with a separation of 1 nanometer. The dielectric material has thickness of 10 nanometers. The side view of the simulated sensor is shown in Fig 3.1. The nano-capacitive pressure sensor is simulated and analyzed for the parameters like displacement, capacitance and sensitivity. The displacement of the sensor shows linear behavior with the applied pressure, whereas the capacitance varies nonlinearly. Further, the results are discussed in the next subsection. SL-No. Parameter size in nm. 1 maximum element size 16. 2 minimum element size 1. 3 maximum element growth rate 1.2. 4 resolution of the curvature 0.4. 5 resolution of narrow regions 0.6. Table 3. Mesh parameters. B. Results and discussions. The core sectional view of the sensor displacement for applied pressure is shown in Fig 3.2. The displacement V/S applied pressure graph is shown in Fig 3.3. From the graph it can be observed that the displacement varies linearly with the applied pressure. The maximum displacement of the sensor at 40 kPa of pressure is around 3.009 nanometers. Volume 9 Issue 05, May 2020. The capacitance V/S applied pressure graph is presented in Fig. Capacitance obtained at the pressure of 40 kPa is around 1.2 ff. 3.5. It can be observed from the figure that the capacitance the developed sensor has a sensitivity of 2.5 x 10 to 6 pf/kPa. Varies nonlinearly with the applied pressure. The maximum. For conclusion, the paper presents design and simulation of a silicon nanowire-based nano-capacitive pressure sensor for human blood pressure monitoring. The simulated sensor has a good sensitivity of 2.5 x 10 to 6 pf/kPa, which is very good. The sensor has a potential application in medical field for patient blood pressure monitoring. As it is in nanoscale, it can be easily mounted into the human body.